Kevin Deierling. I'm the VP of Marketing with Mellanox Technologies, but today I'm really talking on behalf of the IBTA, InfiniBand Trade Association, that we are a member of, and I'm our representative. I also have Idan Burstein here. I'm going to talk briefly more at a high level with some marketing-related activities and sort of the motivation for what we're doing, and then quickly give you over to Idan, both because he's got the more technical meat in the conference, and also because he's got way cooler suspenders than I've ever seen. So what the motivation for all of this is the dramatic increase in both data and the associated increase in performance of the underlying storage media technology. And it was nice to see a persistent memory discussion right before this. In the old days of hard disk drives and spinning Rust, we had sort of 10 millisecond order of magnitude access times. And as you go from the hard disk drives, spinning Rust as I like to call it, to a solid state disk, we sort of get 100x performance improvement. So now we're talking about tens of microseconds or maybe 100 microseconds, but below 100 microsecond access time. And critically there, one of the things that starts to happen is you really didn't care about the network contribution to access. So you add 10 microseconds of access time or a few microseconds, and who cares when you're talking about 10 milliseconds to go move a physical head and find your data on a hard disk drive. Suddenly with solid state disk, particularly NVMe drives, which we'll talk more about, it starts to matter. And that's where RDMA comes in and low latency and all of these things we're talking about. And when we get to NVDIMM, okay, and I use that as a broad classification here, persistent memory even goes faster. Now we're talking about sub 10 microsecond potentially latencies down to microsecond latencies, and the network becomes critically important. So that's the background of what's happening with all of this. What we've seen in the market now is really a move away from traditional storage area network technologies to an Ethernet storage fabric. Again, on behalf of the IBTA, if you look at what we're doing there, it's InfiniBand. That's what the I is in the IBTA, but it's also the organization that defined the RDMA over Converged Ethernet, or the Rocky specification. And going back in time, if you looked at why people built storage area networks over Fibre Channel traditionally, it really was related to three things, which was performance, intelligence, and efficiency. And today, if you look at the same metrics that 15 or 20 years ago drove you to choose Fibre Channel, really today you would choose something like Ethernet. And that is in terms of the price performance in particular, because the two go hand in hand. You can always get more performance if you pay enough money for it. But today we're delivering with Ethernet about 3x the performance of traditional Fibre Channel, the highest speeds, 100 gig versus 32 gig, for example, at about 1/3 the price. In terms of intelligence, one of the things that you're starting to see is all of the work that this group is doing is layering the intelligence of the storage fabric into Ethernet. It's now becoming available. And efficiency really driven from things like RDMA, but also the ability to converge the network onto a single network to support not just blocks, but file, object, and hyper-converged infrastructure. So together, all of that is really driving Ethernet as a storage fabric. And you see that in the market in terms of the growth of network storage is really in Ethernet today. And this is showing on the right here the growth of Ethernet versus the decline in Fibre Channel ports that are shipping. This is not all storage related, but it's actually a pretty significant difference here. I think one of the big reasons is because there is no Fibre Channel in the cloud. If you look at what the hyperscale vendors have done, they're really the first guys out there that have realized all the performance and efficiency benefits of using Ethernet and a converged network that combines compute, storage, and networking all on a single fabric. What we're seeing now is things like NVMe-oF fabrics, which is really natively connected to RDMA and Ethernet, also InfiniBand, of course. Putting my IBTA hat on, it does both. And fortunately, they're really the same. So NVMe-oF fabrics, I think probably most people here are familiar with what that is. NVMe SSDs today are the highest performance solid-state drives that you see in the market. They've basically gotten rid of the SCSI layer in terms of the back and forth protocols. Are you ready? Go find the hard disk and then come back and do an acknowledgement, and really put a streamlined protocol on top of the PCI-Express bus. So eliminated the SCSI overhead, but still then it's direct attached storage, and it wasn't initially designed to be shared across a network. People have tried to share it using PCI-Express, and it has its limitations. It works well within a chassis, but PCI-Express, all of a sudden when you start to look at failover and hot swap and all the things that you need to do to build a true fabric, it falls down. And so we've seen people try multiple times, and then all of a sudden they come back and use a real network, because networks have the characteristics that you can unplug things, plug them back in, they self-discover, they reconfigure, they're very good at sharing between multiple hosts and multiple targets. And so you really need fabric to do that. NVMe over fabric is the way that we've extended the NVMe Flash solid-state drives and allowed them to be shared across a bunch of targets and a bunch of hosts that can share that the way you would a normal storage area network. RDMA protocol is integral to the standard. That was part of the 1.0, which includes the transport binding specification for RDMA for both Ethernet with Rocky and NVMe. So just briefly, how does the NVMe over fabric maintain performance? If you look here, the traditional network stack is using
Yeah.
Oh yeah, that one works. Okay. So if you look at the traditional stack, you're going through the software layers, you're going from a user space application down to TCP/IP, through the kernel, and then to hardware, and through the remote side doing the exact same thing. With RDMA, we basically bypass all of that so that the NVMe commands, the data, the capsules are transferred end to end. And so RDMA is the key to achieving this performance in terms of latency, throughput, and efficiency. Efficiency in the sense that your CPUs are not consumed moving data, running a transport protocol stack, and then become available to actually run the application that you're running, in this case a storage application. So briefly with RDMA, you're moving data directly between user space applications, okay? When people think of RDMA as just the transport offload, the equivalent of a tow engine, but it's actually much, much more. When you write a software process and you do a malloc, you get a pointer back, which is a virtual address. You don't have any idea what your physical address is. So with DMA, there's lots of work that you have to go into to figure out what the physical and virtual addresses is. What happens here with RDMA is it's managed for you by the hardware. And so you can exchange, say, hey, send the data to this virtual address. And the hardware manages all of that in terms of performing the RDMA functionality. And that is critical to allow the hardware and the software applications to work efficiently together. So it's not just reliable data transport, but it's user-level I/O that's using kernel bypass to do that. It's doing the address translation, and it's also doing memory protection. So it was good to hear the discussion earlier where they were talking about the TPT, which is the translation protection table. This is really critical that allows application-level communication rather than going through a kernel to communicate. So all of that is part of RDMA. And again, the benefits are higher bandwidth, lower latency, and more CPU available to run applications, so better efficiency. So at a very high level, if you look at how it works, the RDMA and NVMe actually look almost identical. So if you look here, you've got submission queues that are shared through memory and completion queues. And software writes work instructions to memory, and hardware pulls out of memory. And when it does an operation and completes it, it sends the completion notification back into a circular queue in memory. And so the communication between the target software and the hardware, in this case a Rocky NIC, is through the memory interface. And similarly, it's not accidental that NVMe operates exactly the same way. And what you'll see here is that I've got everything written as software, but basically when you get a completion operation from the hardware, NIC, saying that something's happened, then you can turn around, if you're doing a write, for example, take that completion, look at what's inside of it. You'll say, oh, there's a NVMe capsule, and you'll turn around and submit that to the NVMe flash drive, and it will operate as well. So the two are very tightly coupled. You'll see here I have everything in terms of the communication between those two shown in software. That's really an implementation issue. And you can imagine that there's lots of ways that we can streamline much of this activity to make it more efficient. And so that's really what the rest of the talk will be about from Idan, is talking about some of the ways that we can make these things more efficient and improve on latency and CPU and other applications. So with that, I'll invite Idan up.
You want to see if that lab will work?
I'll try it.
Yeah.
Clip it to your suspender.
Can you hear? Yeah. Okay. Can you hear me? Yeah. Works well. Okay. So thanks, Kevin, for clearing our minds. Now I'm going to confuse you guys. Yeah. So having these interfaces aligned, and especially having this interface standardized, brings a lot of opportunities, right? Because once this interface is standardized across all of the NVMe drives in the world, then basically those things, the RDMA NIC and the NVMe, could interact in a standardized manner. And this is what I'm going to talk about. But for this, I'm going to set the ground with some basic things with these protocols, NVMe and NVMeoF fabrics. So how NVMe works, just at the high level, when an application or a driver or debug device would like to submit a request for the NVMe device, it will write a work request to its queue in the memory, and then ring a tiny doorbell. So it will write a small write request. This write request will be 64 bytes. And ring a tiny doorbell can typically be 2 bytes or 4 bytes, right? Then it's not RDMA adapter here. Then the NVMe device will fetch this command, fetch the data, commit this data into memory, and then induce a completion, right? We've seen also other cases in this conference where the NVMe compliant device doesn't commit data to memory, but do offloads. For example, in Steven's talk 2 days ago. But anyway, the interface remains the same, where you post a small command pointing on the data to be transferred. You ring a tiny doorbell on the hardware, and the hardware fetches these commands, fetches the data, and report a completion to the memory. And maybe an interrupt, depends whether you poll or not, and whether you configure it to interrupt you once writing a completion. And then there is the meaningless completion queue head doorbell that could induce some optimizations, but it's not really useful in the common case where you have queues that are in the same size. Okay, anyway. So this is an NVMe device. This is how it works. RDMA works similar, and it builds upon some simple primitives. One primitive is called the queue pair. So a queue pair is a channel for communication between two endpoints. Now this channel is built upon a send queue, receive queue, and completion queue. So as we had in NVMe a submission queue and a completion queue, now we can also receive things from the device, right? So we have 3 queues: receive, send, and completion. We have connect to establish this connection, and within this connect we transfer some parameters, for example, queue depth, and packet size, max message size, etc. we have registration, which is a way to expose memory within this queue pair in order to do reads or writes to this memory, remote reads or writes. And we have send and receive for communication that are two-sided. If I want to interrupt the other side, then I'm sending a send and receive. If I want the other side not to be aware of my memory accesses, I'm doing reads or writes because they are one-sided. Okay, this is RDMA. So the way it works together, and Kevin touched on it a little bit, is that you can potentially map NVMe queues into RDMA queues, and then into NVMe queues on the other side, right? And abstract it to the operating system as an NVMe device, as an NVMe core device, as we saw, for example, in Christoph's talk on the NVMe Linux driver. And the data is being transferred with RDMA, memory to memory, without intervention of the CPU. And we will see it in the next slide. So this is an example of, I think this is a little bit of recap. I guess many people are familiar with the wire protocol, but I just want to set it in order to, because I'm going to make things complicated a little bit in the next slides. So make sure everyone are aligned. So NVMeoF Fabrics I/O write, how it looks. The NVMe initiator or host or whatever name you have there will send a tiny command. A tiny command is a 64-byte command carrying a pointer to the actual data into the target or subsystem or controller. Again, depends what terminology are you using. Now, when the RNIC will get this message, it will induce a completion and maybe an interrupt. Depends whether it's user space, kernel, or polling, or interrupt based. Now this the controller side, we need to allocate some memory for fetching the data, and then maybe register this memory if it's unregistered, and then fetch the data with RDMA read. Now, be aware that this side is not aware that the RDMA read has occurred. It only registered this memory. Now, when the whole transfer will be done, you can imagine, for example, this transfer will be 1 megabyte. Then, after the whole 1 megabyte has been done, it will induce, the RNIC will induce a completion. Okay, so we have one interrupt for completion on the command and one interrupt for completion for the data transfer. Now this device, now the controller side will need to somehow commit the data into memory. If it's an NVMe device, it will need to post a command and ring a doorbell like we've seen before, and then and wait for completion. When it gets a completion, it will need to send a response to the initiator or host saying, we're done. This response will trigger a completion on the RNIC side. Now the host can see the completion, see that the completion, verify that the completion status is okay, and free its buffers and invalidate the memory region in order not to be accessible from the outer world. Okay, so the transaction is done. And basically, this is great, right? And we've seen through this conference many reasons why it's great. For example, it's great because it provides 1 million IOPS per core, or 1.3 million IOPS per core in SPD fucking K, right? So this is one. So this is one reason it's great. Another reason that it's great is that its CPU utilization with respect. This is a paper published by Samsung in the conference Systor. Its CPU utilization is much less than iSCSI, and it's really similar to local access. So you basically don't pay a lot for this aggregation, or however you call that. Another reason that it's great, this is again from the same paper from Samsung, is that that you can see that it has some implications on latency, right? So we've seen numbers across this conference: 10 microseconds, 12 microseconds, 6 microseconds. Depends on how you measure. But these numbers, when you go to high load numbers, which are real use cases, right? You see that the latency meets the latency of directly attached, and even better. and even better numbers. And this is an indication that this protocol is great, right? So you basically you can use this protocol and without paying anything in terms of real actual performance, not benchmark single queue depth performance. Yeah, and this is another graph of the cumulative distribution, right? No, it's the latency across IOPS. So again, we see that the RDMA, where is it? The NVMF average latency and the DAS average latency, they do have a difference in 0 queue depth or 1 queue depth, right? But they don't have any difference on the high IOPS numbers. So the transport doesn't matter. You just gain sharing and you gain disaggregation on the network, on a real network. So what are the challenges? One challenge is scalability. So assuming you converge your storage system into one node or into B on the network, then now many hosts could access your device, right? So many hosts mean many calls in many hosts that could access any device you have in your system. So if you have 24 drives and there are 16 hosts and each one of them has 48 cores, then you end up having thousands of connections. Now, connection by itself, it's not a huge context. It can be 256 bytes. So it's not something you cannot really maintain. But what is hard to maintain is the buffers that you need for receiving commands per each connection. This is a real problem. Because you want these buffers to be enough for getting many messages, right? But you don't get in parallel many messages from all of the connections, right? At the end, you have one port that is transferring one packet at a time. So a way to resolve this scalability problem is by having these receive queues shared across many queue pairs. And the implementation in Linux up until a few weeks ago was that if you use this mode of shared receive queue, which is good for scalability, you break what all the marketing people are saying on NVMeoF fabrics. Why I'm saying that? Because the implementation was I have a single shared receive queue for all of the system. Now, instead of having the parallelism that you're supposed to get from NVMeoF fabrics, you need to lock in order to post-receive in between the cores. So we enhanced it, and please try it. So we submitted patches for having multiple shared receive queues per target in the NVMeoF fabrics target in Linux. So you can have a shared receive queue per core. And we also plan to have to enhance this even further in order to, for example, adjust the queue depth according to the latency. Those things play together, right? Because if your queue depth is too small, then you cannot have as many commands as you need for saturating the device. But if your queue depth is large enough, you pay a lot of memory footprint. So there is a need for adjustments there. And you can learn the right size. Okay, so this is one thing. Please try it. I would like to discuss how things flow through the system in an NVMeoF fabrics target. And this is where it gets confusing, right? So bear with me. So in a system, you will have an RDMA NIC, an NVMe drive, and maybe a PCI fabric. This PCI fabric may be located at the host root complex, maybe with a PCI switch. And within the host memory, you have these queues that we are talking about, right? A receive queue, a send queue, a submission queue, a completion queue, and some data buffers. The data need to be somewhere. Okay. Yep. So now it gets complicated. But I have numbers here. I have numbers here. Boom. Yeah, that's correct. So I have numbers here. So the first thing that will happen in such a system is that a fabric command will come from the network on a specific queue pair to a specific receive queue. Maybe it's shared, maybe not, and will be scattered to memory. This command can be tiny, right? It's 64-byte command saying I want to write to the media. Okay? Keep in mind that my example is always NVMe write. Okay? It applies for reads, but I keep the right example from previously. So I got a fabrics command. This is the first thing I got. Now we see in this fabrics command, I see a memory region, a virtual address, a memory region, and a length, right? Of the data that I need to write. So I go and fetch this data. So I need to post the RDMA NIC, a command of RDMA read, and this RDMA NIC will transfer a read packet to the initiator, and the initiator will respond with read responses. So this is the second bullet, the data fetch. And I will get the completion at host memory once this data fetch is done. Once this data fetch is done, now I have the command and I have the data. Now I need to do some minor manipulations to this command, like for example, making the pointer of this command not a fabric pointer, a local pointer, right? Because this device is local. It knows PCI and physical addressing. It doesn't know memory keys and RDMA. So I'm going to manipulate this command and then post it to the NVMe submission queue. This is number 3. Number 4, I will ring the doorbell. I will ring the tiny doorbell, the 4-byte doorbell. And now the device will start working, right? So first thing, the device will fetch the command. So this is one round trip on this PCI for just fetching the command. Another thing, the device will fetch the data. So another round trip for fetching the data. And then the device will induce completion once it's done, right? After this completion will be posted, either if I'm polling or I'm an interrupt-based software, I'm going to need to post a response capsule for the initiator. So I'm going to post this completion, or maybe a manipulation of this completion, into the send queue of the RDMA, and then it will be sent to the initiator, and this transaction is done. So it's not that complicated, right? But what are we seeing here? We need to see that the data is transferred once to the memory subsystem and another time to the NVMe device. So the bandwidth of the memory subsystem here has to be twice the bandwidth that you want to saturate. So if you want 100G to this NVMe device, if you have devices that are supporting 100G, then you need 200G memory subsystem. If you have 24 drives and each one of them can support 25G, then you need 48 25G bandwidth of your memory, which is, there are no such solutions in the industry right now. So this is a real problem. And for these problems, for these kinds of problems, there are all this standardization in NVMe of how to resolve them. So an example for a feature is a controller memory buffer, where the internal memory of the NVMe devices, they have memory, right? They have memory. They need memory for FTLs. They need memory for write buffers. So if this memory could be exposed on the PCI, which is a controller memory buffer, then we don't need a lot of it. So just a quick calculation, which I hope is okay, but it's at least the order of magnitude, is that in order to buffer 50 gigabit Ethernet to 200 microseconds, you just need 2.5 megabytes. So double it or make it 4 times, but it's not gigabytes. And the device has gigabytes. It must have gigabytes because it has terabytes of data it needs to maintain the metadata for all of this data. So if you enable to expose this memory into the PCI, then you can enable peer-to-peer communication of data and maybe also commands. So this feature is optional from NVMe 1.2, and there are devices that support it, and we are also demonstrating the use model of that. So let's see how the data flows with the CMB. So again, same thing. I got a command. Now I'm going to issue a read request to my RDMA adapter. So the blue line here, I'm gonna have the my scatter pointer, I'm going to have them on the NVMe device. So now this adapter will read the data from the initiator and write the data, the response directly to my NVMe device. So keep in mind that the data didn't go through host memory at all. And everything else works the same. I'm going to get the completion to host memory. Now I'm going to reformat the submission queue entry. I'm going to ring a doorbell. I'm going to wait for the NVMe device will fetch the command. And then it won't need to fetch the data because the data is already there. It may need to fetch the data from its own memory, but not through the PCI. And then it will induce completion, and I will send a response. So what we have here is same approach, same software. The only difference is that the NVMeoF Fabrics implementation, the target one, has to know that this guy has memory and register somehow this memory, get this memory to their get the authority to access this memory and to register this memory into the network adapter, and that's it. And we reduce the load, and by that we reduce the significant load. So for each like 4K or 8K or 64K or megabyte transfer, I get 64-byte command to host memory, and that's it. So now I don't need high bandwidth host memory. I may need its processing power for doing the IOPS processing, but I don't need the bandwidth, which is really strong. Now, how do you do software for that? How do you do that in Linux? How do you enable in Linux a driver to provide memory to another driver? Yeah. So this is how you do that, right? You got a guy with suspenders and hat to talk about it with Christoph, but there is a discussion on that at 4 p.m.
I think it's sometime around there.
Yeah, whenever one of you will be at the flight, Stephen will talk about the Linux implementation for for peer-to-peer. But the main idea there is having an agent, or whatever you call it, in Linux that is coordinating between drivers that want to subscribe and unsubscribe others' drivers' memory.
I guess to add, there's a public domain fork of Linux that turns all that on. If you're interested, just find me on LinkedIn and I can send you a pointer to where it is.
Mm-hmm. Yes. So, but this is a generic approach that will enable such ideas to work as well with GPUs, with whatever drive, NVRAMs, whatever drives that you have that expose memory and want to interact with another drivers. Okay? Okay, so we went through the reduction of the memory subsystem bandwidth. Right? This was our purpose with CMB. Now we can have other purposes. So some companies are offering offloads for the protocol and the protocol translations to the standardized drive. So the reason to do that, there are some reasons to do that. One reason, which is quite obvious but could be debatable, in its efficiency, is offloading the CPU, right? You don't want the CPU to do these tiny management things, right? Now, if the CPU need to process each and every I/O, then your CPU could be the limiter for the number of IOPS you can achieve, right? Another reason is latency. Triggering the CPU, if it's interrupt based, then it costs you with that amount of latency, and with the next generation drives where the latency goes down and down, it could be significant. Another thing that you get, which is a true value, that is the resiliency for any problems that could be at the host level. So, for example, if there is a kernel panic, then you don't get any errors. And another important.
This is going to keep working with the operating system.
Yeah. So let's discuss this. But anyway, the fact that the I/O operations are being could be terminated in an offload agent could create independency between the offload and the operating system. And an important fact, mostly for HPC guys, and we've seen this as one of the main drivers for this technology, is the fact that it's reducing the operating system noise for applications that are running at the host. So one typical deployment of NVMe could be, I have my data center. I have NVMe drives in each one of my servers, and I want to share them because one need half a drive and another one need 2 drives, right? And I don't want to pay operating system noise or CPU processing for that. I don't really care about the millions of files. I just want to share my drives because each endpoint on its own doesn't really affect my my performance as all of my data center, right? Because it so there are some use cases for that, and some companies that are solving that. And the question is, how does it work? Yeah. So again, the complicated chart. Now we are getting a Fabric command. Now the processing is being done in the adapter, right? So the Fabric command needs to get into the adapter, not to the host memory. Keep in mind here, it's not assuming CMB, this example. Okay? Not assuming control memory buffer. So you get your command into the adapter that needs to process it. Now you have an agent that is on top of the transport that is processing Fabric's command. Now this Fabric command is being received. Now someone needs to fetch the data. Who is this someone? This offload agent, right? So it's going to allocate memory that was allocated to the network adapter in advance, and it's going to fetch the data into this memory. When the fetch is done, it's going to get indication, like those indications are within the RDMA, within the RDMA NIC, and then it's going to take this Fabric command, manipulate it, and write it into host memory into the NVMe submission queue. Okay? Once the command is in the NVMe submission queue, it can start its polling on the NVMe completion queue and submit a doorbell. Now this adapter will hang polling. It's hardware, right? So it doesn't hang. It's not like a CPU that hangs and doesn't do anything else. So it has a machine that hangs on the CQ. It triggers it and then trigger a doorbell. Now the NVMe device will do its work similarly to how it has been done without this offload, right? And without the CMB. It will fetch the command, fetch the data, and write the completion. When the completion will be written, this guy will see the completion on its polling machine.
Polling on host memory.
Yes.
TLP needed.
Yes. Yes. The rates here could be discussed, but in general it pose, and it can do the things that you are doing in the kernel as well, like the heartbeat polling. Anyway, when it gets a completion, it needs to take the completion queue entry itself that is already in the adapter because of the polling, right? And then return a response capsule to the host saying transaction done. Okay? So this is the workflow. And now you have, again, in this case, because the NVMe device doesn't support CMB, you still have all of the bandwidth go through the memory subsystem, but you don't have any processing for I/O, which is great. Now, how you would do that, how you would implement that in Linux. So this is, again, a very similar problem to the problem that you had with CMBs. We need one driver to share information with another driver. But now this information is not memory. Now this information is queues, it's page size, it's doorbells, addresses. Okay? So one approach, which was our approach in the way we work today, is go through the block device in a specific way of working with, of solving this specific problem, and get these properties for queues and get these properties for the device itself, and then register them to the connectics. This is one approach. I think that a better approach will be to converge in a generic way, similar to what was proposed for peer-to-peer memory. Define something that is generic, like peer-to-peer queue association, or peer-to-peer PCI bar association, and have a generic infrastructure for doing all of these, Christoph will call it stupid things, in the kernel. Okay? Yeah, I don't have enough time to talk about namespace virtualization, but we support namespace subsystem virtualization and controller virtualization in our adapter. So within this offload, we can expose to one drive to many hosts. We can take many drives and expose them as a single drive. And this can be, if someone wants details, he can contact me. So some performance numbers here. So we are developing this solution throughout our product line. This is an example of ConnectX 5, which is doing 1 million IOPS, and again without any CPU utilization. And you can see that in large block sizes, you have basically full wire speed, this including the headers, and without consuming any CPU utilization. And this is important for some of this technology use case. The latency is improved, not that significantly. I don't think it's that important, because under load, it doesn't really matter. This is just an example of how much CPU you will need to do the same thing we are doing without any CPU utilization, but it's obvious. We're doing that in the adapter, therefore you don't consume CPU. Clearly obvious. Now this figure with NVMeoF fabrics, target offload, and CMB. Yeah, this is Christoph's favorite, I think. So you get a fabric command. You receive this fabric command in the receive queue. Now the offload engine sees this command, needs to understand, okay, I need to bring memory. I need to bring the data, right? And I need to allocate some place in the data that was registered for me in advance. Apparently, this data is in the NVMe device, but for me, I don't care, right? So I allocate a memory with my memory allocator and fetch the data into the scatter entry that was allocated to me. Now the data is located in the NVMe device, right? When I get a completion, the data is located in the NVMe device. I trigger a poller, and then I trigger a doorbell to the NVMe device. And then I need to reformat the NVMe command. But now, instead of reformatting it into host memory, I'm reformatting it into the NVMe device, making it pointing on the CMB. Then I trigger the poller, and then I trigger a doorbell. Now the NVMe device works just as it works with the CMB. It fetches the submission queue entry. It sees that the data is in the CMB. It fetches the data from the CMB, and then it generates a completion. Once the completion is posted, my poller will see this completion, and then it will return a response capsule, and the I/O operation is done.
So why don't you put this NVMe completion queue into the RDMA? Then you don't
This-
need to the
I didn't want to overcomplicate these slides, but apparently there are RDMA NICs that support CMB. It's not called C. It doesn't. It's not called CMB in RDMA NICs. It's called in-network memory or whatever the other marketing guy will invent. But memory buffer, RDMA memory buffer. But those guys have memory too. So the data could be potentially located here. The CQ could be potentially located here. I think the main difference between these guys and these guys is that these guys must have DRAM. They must. They need gigabytes of metadata. These guys, depends on the implementation.
Actually, it's not changing much. It's just putting the arrows the other way around.
It's changing a lot. It's changing a lot because these guys.
No must. There are DRAM-less NVMe controllers. You're probably not excited about them because they're tiny consumer things, but they exist.
Yeah, I agree as well. But I think the main difference between those guys, another difference between those guys is that this is commonly high bandwidth, and this is commonly low bandwidth, like lower, right? It can be by 4 PCI, and this can be by 32 PCI, or by 16 PCI. So eventually, distributing this memory across drives will make it more scalable. And the fact that these guys mostly have memory in them. Yeah. So with this technology, with the combination of CMB and the target offload, you basically have host memory just for doing the management. It's creating the QP, registering the memory, doing all of the peer-to-peer abstractions for being compatible to all of the drives in the world, but it has nothing to do with the data path. That's it. Yeah.
Yeah, I just wondered if you could go back for a second to show the write latency for low Q depth.
The latency for low Q
So
depth.
that's about 7 microseconds. The NVMeoF fabric write latency.
Yeah.
Yeah. Okay. Thank you.
Yeah.
It's quite good.
What's the fabric
That's,
speed?
that's,
Yeah.
What's the fabric speed on your charts?
So again, sorry for this is added latency, right?
Yeah.
It's not latency to the drive. It's added latency local with compared to remote. Yeah.
Was that a 100 gig fabric, or how fast was that fabric?
100 gig. Yeah.
How
Yeah.
large do you expect the CMB to be?
What?
How large the CMB should be? What should be?
Yeah. So I had a slide on that, right? Yeah. So you need to calculate the 200 microsecond times 50 gigabit Ethernet, whatever your device is supporting, and times it by 4 because magic. But in general, it's order of magnitude of tens of megabytes would be fairly enough. Because you just need to buffer the latency of the drive. Now, if your drive is a drive that could create latencies of 2 milliseconds in a high probability, then you need more. But if you have average latency that is mentioned here, then it's tens of megabytes.
Because this would play into how Tom was talking about earlier, if you need to persist things, because if this is a volatile space for the memory or the NVMe drive, you would have to make sure that it needs to get written to the flash
Yeah,
or whatever.
I'm making sure of that. I'm submitting a submission queue entry, and I'm getting a completion, right? This is the way.
guaranteed to be consistent and atomic, right? Because the CMB is not, it's not that, it's not the persistent.
The CMB is not the underlying memory.
For host memory. Only when you get the NVMe completion back do you know that that write was atomically done to the essence.
That's correct. Anyway, thank you guys. We're out of time.